We will now discuss Monte Carlo estimation of integrals. This is a very important topic and you will need to use it in your homeworks. Let me show you some of the images that can be produced using Monte Carlo path tracing. This example of a car under a uniform hemispherical light source shows you how you can produce these kinds of beautiful soft shadows. This example is seeing the caustics under this glass ball, and this is produced using 1,000 parts per pixel. You'll notice there are still these bright spots which are often known as fireflies that have not yet been removed, and you would actually need more parts to completely remove the noise. We go back to the challenge of estimating the average. The advantages of Monte Carlo are that it is robust for discontinuities, it converges reasonably efficiently for large numbers of dimensions, it can handle complex geometry and complex integrals, and it is relatively simple to implement and reason about. We can make this a little bit more formal. We seek the definite integral, which is the integral of f of x dx. We replace that by the expected value. When we talk about an expected value, it's the integral of f of x with samples drawn according to some probability distribution p of x dx. Now you'll note that this expected value does not equal to the original integral unless p of x is equal to 1. For now, assume that p of x is in fact equal to 1 and is a uniform probability distribution. In this case, the random variables x of I will be drawn proportional to p of x, and we find an estimator y of I, which is the function f evaluated at the samples that are drawn are the random variables x of I. We can then define this estimator as simply the mean of the yi values. This is very important in Monte Carlo integration or Monte Carlo estimation, that you have an estimator which is then evaluated at the random samples you are drawing. To get a little bit ahead, in order to make sure this f of x dx corresponds to the original integral, we actually need to divide by the probability of x so that p of x and p of x will cancel out. In the general case, the estimator will actually therefore evaluate f of xi and divide by the probability. In this case, because the probability is uniform, we can omit that step. But in general, for any Monte Carlo integration, the estimator will be f divided by p. Here is a simple example of directional sampling for direct lighting, which is analogous to what you will be doing in your homework. In this case, we are integrating the irradiance is what we want to find. We are integrating over the lighting and the projected solid angle. What we can do is sample the hemisphere uniformly. The hemisphere has 2 pi steradians associated with it. The entire sphere has 4 pi steradians. Therefore, the probability of actually sampling any particular direction in the hemisphere is 1 over 2 pi. Remember that I said you have to normalize by taking the function value and dividing by the probability. The division by 1 over 2 pi leads to this multiplication by 2 pi here. Apart from that, this is simply the function value L and cos theta. Now, what is the value of L here is the radiance coming from the point you hit, which is x star, in the direction of minus omega n. So this is a simple estimator that can be used either for direct lighting, if L of x star corresponds to a light source, or even for indirect lighting in the context of path tracing. Now that will give you the estimator, which will ultimately enable you to render your images. However, one thing we care a lot about in the context of Monte Carlo integration is a notion of variance or error. We define the variance as the function value minus the expected value of the function squared. So in a sense, this is the mean squared error. You're taking the error, you're squaring it, and then you're taking the mean over a number of samples. The standard deviation would be defined as the root mean square error or the square root of the variance. One of the key properties of Monte Carlo integration is that the variance decreases as 1 over n. So the variance for n samples in your estimator is 1 over n times the variance for a single sample, which is simply the variance of the function f of x. What this means is the standard deviation of the root mean square error decreases as 1 over square root of n. These decreases are not that substantial, and therefore Monte Carlo integration actually converges more slowly than the standard rules like Simpson's. However, Monte Carlo integration converges at this rate for arbitrary dimensions, while standard integration rules get exponentially worse. And it also handles discontinuities, irregular domains very well. Therefore, increasing the number of samples removes noise slowly, and indeed much of the work in computer graphics rendering since the development of the rendering equation has been about how to reduce the variance in Monte Carlo integration. We will talk briefly about two possible methods, which are importance sampling and stratified sampling. Importance sampling is a very simple idea. Simply place more samples where the function f of x is bigger. In this case, the function f of x has two peaks, so instead of distributing samples equally, put more samples at the peaks and fewer samples elsewhere. The estimator still follows naturally. The estimator is always the function value f of x divided by the probability of xi. This is a very useful thing to know in computer graphics. You can choose any function p of x for importance sampling, and all you need to do to get an unbiased estimator in Monte Carlo rendering is define it as f over p. It's very important to know this idea. We can go through the formal mathematics of this and show that it is unbiased. So if you integrate against p of x, the p of x cancel out. Notice that p of x can't quite be equal to 0 because f of p would go to infinity. And so typically one wants p of x to be non-zero everywhere. You end up with the original integral, and so the expected value of this estimator is still the original function, independent of whatever probability distribution you choose. However, you want to choose a probability distribution that will reduce the variance. And in fact, if the probability distribution is chosen proportional to f of x, then the variance is actually equal to 0. Because yi, which is just f over p, but p is now proportional to f, let's say p is equal to some constant c times f, will simply be equal to 1 over c, and therefore how many ever samples you take, there is no variance at all. Even taking a single sample gives you the result. The question now is, why can't I always do this? I pick a probability distribution proportional to f, and now I have 0 variance. This is such a great idea. There is a catch, as there always is. So one challenge is whether you can actually generate a probability distribution proportional to f. But even if you can, here is the challenge. I talked about this constant c. This constant c is needed because the integral of p of x dx has to be equal to 1, while the integral of f of x can be arbitrary. And finding this constant c, because the constant c, as you can imagine by doing the algebra here, is equivalent to finding the integral of f of x dx, which is the original problem. And therefore, simply evaluating the constant c to get the probability distribution is equal to solving the original problem. Therefore, one cannot typically choose p of x proportional to f of x, but one can choose p of x which is close to f of x, and the closer it matches f of x, you will have less variance with better importance sampling. The second variance reduction strategy that I want to talk about is stratified sampling. In this case, you divide into separate subdomains. For example, you may have one subdomain corresponding to the first p, a second subdomain which has low values, a third subdomain corresponding to the second p, and a fourth subdomain which has low values. You estimate the subdomains separately, often with only a single sample. Because the variance is less in each of the subdomains, the net variance from stratified sampling is less. Typical way in which you can do this is break the light source into a 4x4 grid and send one sample to each point on that 4x4 grid. This is using 16 samples to sample the light source using stratified sampling. In fact, one can also combine stratified importance sampling by stratifying the random number generator you use for the inverse CDF sampling. In practice, both stratified and importance sampling are key tricks you need to use to reduce the variance in your computer graphics images. These images are from Arvo, where he shows how to do stratified sampling over an arbitrary spherical polygon. Note that stratified sampling is unbiased because one is simply estimating each subdomain separately, and if the estimate on each subdomain is unbiased, then the net result is unbiased. In this case, you are estimating over some m subdomains. Ni is or nk would be the number of samples in each of the subdomains. One can also do an analysis of the variance without going too much into the math. If the variance in each of the subdomains is less, then the total variance will also be less.